Welcome to CS210, where we're going to build our ALU. Now, you want to add a new circuit and call it ALU. Now, I've actually already built the full CPU inside of this, so I can't call mine ALU. I've called mine ALU build. Anyways, you get a new blank circuit, and you can click just once on your ALU bit, and you can place it down. Now you can see I've clicked up here when I'm on my ALU bit, and I was able to edit my circuit and make it look really nice. So I have bus 1 and bus 2 going in up top. My operations here on the left side, my C-in over there too, and my outputs, C-out and bus 3 coming out down the bottom. So you can edit yours however you like, but it's nice to edit it and make it nice and labeled. It'll help you see things better. So now we need to introduce the concept of a bus because we have bus 1 and bus 2, and they each have 16 of these switches. So you might imagine that you could grab 16 of these switches and say, okay, this is bus 1 bit 0, and then grab another switch, bus 1 bit 1, bus 1 bit 2. Now luckily, Logisim has something built in so we don't have to drag out all 16 of those. Just go ahead and select your input switch and notice it says data bits over here. You can change that to 16 and it turns that one switch into 16 switches all connected nice and neatly together. And you can see you can use your poke tool, this little finger tool, to change the value of each one of those switches. So but the only difference is now when I drag this wire down, that's 16 wires that I'm dragging all together. By the way, you're able to rotate these using the arrow key. So I rotated this so the wire comes down right here. Now, as you can see, if I try to hook 16 wires up to this single wire that I'm dragging from my ALU bit, that Logisim is going to get confused. And it's telling you 16 here, and if you could see it, there's an orange 1 right there. It's like, I don't know how to hook 16 wires up to a single wire. And that's why it's giving you that orange sign. So whenever you got the orange sign, you got a lot of wires in here and a different number of wires in here, and it just doesn't know how to connect it up together. So how can we do that? Well, over here in our wiring, we have a splitter, so we can pull this splitter out and place it down. And the splitter starts out with a bit width of just 2, so we can change that to be 16. And now the splitter has 16 wires coming out of it, and we can connect it up. Now inside here, it knows that this is bit 0, or the least significant bit. This is bit 1, 2, all the way up to bit 15, the most significant bit. And each one of those wires is labeled. So if you zoom in really closely on this splitter, you can see that bit 0s through 7 goes out on this wire, and bits 8 through 15 go out on that wire. And what we can do, though, is click on our splitter, make sure you got the splitter, and instead of fanning out to 2, so now we have 8 wires coming out here and 8 wires coming out here, we can fan it out all the way to 16. And that'll give us 16 different outputs that we can use. So now let me just organize this a little bit better. And all right, you can kind of see that these are individual wires and they're the values of these switches. So you can see if I toggle this switch, it turns that wire on and off. And I toggle this switch, it's turning that one on and off. Of course, the most significant bit turns that one on and off. So now we can grab a tunnel just from your wiring. That way we can label each one of these 16 bits. So we need to fan it out 16, and then we can grab this tunnel and grab your edit tool over here. And the tunnel should be a data bit width of 1. By the way, you can make these tunnels so that you can tunnel the entire 16 wires off together. And you might want to do that in later labs, but in this lab we want to separate out each individual wire because they need to go to their own individual ALU bit. So what I'll do is I'll take that tunnel, I'll connect it up, and I'll label this. This is bus 1 bit 1. So you can come up with your own naming convention, but I just did B1 hyphen 1. And actually, I should do hyphen 0 because that is bit 0. Now, when we do that, we're probably going to need a lot of room. So we should then grab another tunnel. And once again, this is bus 1 bit 1. And then I'll need to do that for all of them, all the way up to. So now I'll grab this this tunnel here. And we can do that for bus 1 bit 15. So now we have, and you'll have to do that for the rest of these. I'm not going to waste your time in showing you, but you just need to hook up a tunnel for each one of these. And you could go into your input switch and call this bus 1. So there we go. And now we need this for bus 2 as well. So you might think, okay, drag one of these out again, make it 16, do all this over again. Well, it'd be really nice if we could just copy and paste. So yes, you can copy and paste. Just grab your edit tools, select the entire thing, hold down Command C or Control C if you're on a Windows machine, and Control V to paste. So you just copy and paste this. And now we can change that input to bus 2. And you can see it's kind of getting a little upset. That's because over here, we're trying to make this says the bus 1 bit 0 should be a low voltage. And this one says that it should be a high voltage. So whenever you get the red lines, that means you have two outputs and they're trying to drive this wire, trying to make it a different voltage. And it doesn't, Logisim's like, I don't know which voltage to make this. Is it a low voltage or a high voltage? In real life, if you're doing this with real electrical circuits, there's nothing that turns red. It could be that your circuits get fried and a little smoke goes up if you hook two outputs up together, or it could just be that the logic stops working, and it could be really hard to debug. But anyway, we just need to come in here and relabel these bus 2 bit 0, or bus 2 bit 1, and this one's bus 2 bit 15. And so now, hopefully, after you've connected all 15 up, you could just copy and paste, and then it's pretty easy to click on each tunnel and edit them all the way up. And now we're going to need one more of these for our bus 3, except for it's an output pin, but don't let that dissuade you. You can just copy and paste one of these and make sure you select everything. And in order to select everything, we have to get that label too. So copy and paste it. And if you ever do something weird like that, like I just dragged the wires to the full thing, just Control Z to undo, grab on a solid surface, and we can pull this guy down. You'll probably need some more room. So if you ever need more room, just zoom out a little bit, and then we can drag this guy down. And now we can delete the bus 2, grab an output pin, and it has data bits too, so we can make that as 16 output pins instead of just 1. And connect it up to our output, which we'll label bus 3. Okay, and then we got to go in here and relabel each one of these to be bus 3 bit 0, and this will be bus 3 bit 1, all the way up to bus 3 bit 15. Okay, so now that we have our 16-bit inputs, our 16 over here, bus 1 and bus 2, and our 16-bit output all set up, now we need to grab our inputs for our operations. So we have our 9 operations, so we have add, and I recommend just putting a tunnel on these because we're going to have to drag these inputs to all 16 bits, all 16 of our ALUs bits. So we can just go ahead and tunnel that. Remember, you can also highlight a tunnel, copy, paste, and rotate it over and do that. Now, be really careful that you get those wires connected. It's always a good idea to just drag something a little bit, make sure the wire follows it, because sometimes you think you got it connected, especially when you zoomed out. It's close, but not quite connected. And if you drag it, you can see, oh yeah, I didn't quite connect that. So that's one nice little debug thing you can do to make sure you really get your wires connected. And then once we have all 9 operations, so we need the rest of these: add, subtract, two's complement, and, or, not, shift left, shift right, and traverse 1, connected up to this guy right here. And then we can also grab some tunnels, and these tunnels will save you a lot of time. So let's say this is bit 1. Let me move it over and highlight all of this. So let's say this is bit 1 right here. So this is bus 1 bit I right here, but now the I is going to get replaced with 1s. So all we have to do is take our tunnels, place it down. So that is bus 1 bit 1. And so we connected this wire up to there. And then another tunnel for bus 1 bit 2. So remember, I is 1, so I plus 1 is 2, so this should be bus 1 bit 2. And then another tunnel over here, so this would be bus 1 bit 0, because I is 1, and now that's 0. Of course, we're going to have another one for bit 0 and another 13 for bit 2 through 15 going here. And you could put them 4 and then another row 4, or you could just string them all along here and have a nice long row of 16 of these guys. And grab another label for this guy right here, and that is bus 2 bit 1, because I is 1. Grab another label down here, another tunnel, and use my arrow key to rotate that around. This is bus 3 bit 1, because this is bit I right here. And now let's say that you have all 9 of your operations hooked up. We have all of these guys hooked up. Then highlight it, copy, paste, place it down, and then you could go through and start editing this. So this is bus 1 bit 0. So this would be bus 2 bit 1. Okay, this is bus 2 bit 0 right here. And this is bus 3 bit 0. And hopefully you have all the adds, all your operations hooked up to your input switches. And you can grab your C out if you want and drag it over to the C in of the next one. Or you can use a tunnel to connect those, whatever you want. And now we have 2 of them done. So now copy and paste and do it for bit 2 as well. All right, so after you've copied and pasted for bit 2, 3, 4, 5, 6, all the way to bit 15. So you're missing bits 3 through 14 here, and now pretend this is bit 15. Now, if you notice, the math stops to work on the 2 edge cases, because this is I is 15, but 15 plus 1 is bit 16. There is no bit 16 over here. And also over here, the math doesn't work out because there is no bit -1 from bus 1. So this guy and this guy will not have an input. So we'll need to put something in there for both of these. Now, finally, the C out, this CN will get the CN from bit 15. This very last C out will not go anywhere. So this is only for debug purposes only. We can put the very last C out here, and that way when we're looking at our computer and if it isn't working right, we can tell what this very last C out is. It might help you, might not, but might as well. It's just a wire hanging there if you leave it, but we'll just bring out that C out as an output. And also, the very, very first bit will not have something on its C in input. So we'll have to figure out that. So there's still 3 questions remaining with this. What do we do with bit -1? What do we do with bit 16? And what do we do with the very first input on this CN? Well, remember when we're taking the 2's complement or subtracting, that we've only added 1, or we've only inverted the bits and we never added 1 to the least significant bit. And the least significant bit is bit 0 right here. So when we're subtracting or taking the 2's complement, then we want this to be high, turn this voltage to high, and that'll do the add 1 right there. So all you have to do, and the logic kind of the same thing as the logic built in to your lab before, was 2 input OR gate. We'll make this a narrow OR gate. Hook it in and hook that up to subtract operation and your 2's complement operation. That way, if they turn on subtract or 2's complement, the voltage on here will go high, and that will add 1 to your 2's complement when you're doing that. So there's that input. What about this right here? Now that's done when we shift to the left. So we're taking our number, we're shifting it to the left. What goes into the least significant bit when we shift to the left? Okay, just looking at our programmer's reference, and let's go ahead and look at our shift left operation. And it actually has the hint up here. So we're taking the number, we're moving it this way, and what shifts into the very least significant bit? Well, it's always a 0. We always just put a low voltage there. Now let's look at shift to the right. What's going to go into the most significant bit? Now, we want to preserve the sign. So if this is our number, and remember this is the encoding, but pretend that this is the number that we're shifting to the right. Because this is a high voltage, we know this number is negative. If we shift this to the right, then this one will come in here. If we replace it with a 0, then we've turned our negative number positive. And we want to keep it negative. So if this is a 1 and we shift it this way, we want to shift a 1 in there. But if this is a 0 and the 0 shifts over here, then we want a 0 to shift in to keep the number positive. So, and that's right here, sign extending the most significant bit, and that's to preserve the sign, keep negative numbers negative and positive numbers positive. Well, down here we have a little hint. Notice bit 15 will show up twice. So whatever bit 15 is, it shifts off to bit 14, but it also shifts back into itself. So this bit 15 is lucky. He'll go to bit 14 and he'll get copied to himself. So bit 15 wants to get shifted in to bit 14, so we could just connect it up like that. Now the other one over here, bit 14 that I don't have in my circuit, will also get bit 15, just like this bit 1 got bit 2. So 15 will show up in 2 spots. Now what about the constant 0 to shift into there? Well, you could click into the wiring and there is a constant and you can place it down. It's just 1 data bit. If you wanted it to be a constant high voltage, you can put that there, or a constant low voltage, whatever we want. And we can just connect the little dot up there is the wire that we can drag out of there. So we can rotate this around and we can connect it up to that wire. So there, now we have bit 15 shifted up. All right, almost done. There's one more output that we need. In order to make branching decisions, we need to know if all of the voltages on bus 3 are low. If the output of my ALU is spitting out the number 0. And that'll help make decisions like branch greater than 0. We don't want to branch when it's equal to 0, only when it's greater than 0. So we can't just look at the sign bit of what's coming out of our ALU. We have to look at every single bit and make sure they're all low. So there is going to be one more output, and the output's name is going to be called 0, and it will be high when all of the bits are low. So you're going to need to put a gate. a gate. I don't know which gate. I'm just putting one down. You're going to have to figure this out. You can figure it out using 2 inputs and then expand it to using 3. But when you click that gate, number of data bits just 1, but the number of inputs you can go down to up to 16. That way you can compare all 16. And if all 16 of bus 3 bit 0, all the way to bus 3 bit 15 is a 0, if all of them are a 0, then this voltage should go high. If any one of these turn to a high voltage, then this should be a low voltage. So you're going to have to figure out what goes in that spot right there. And yes, you're going to have to copy these tunnels, all bus 3. You're going to have to copy these bus 3 tunnels to feed into the inputs of all 16 of these bits. So then once you have all of that done, you're done with your ALU. So you can click the plus button, add a new circuit, and then you can grab your ALU down. Of course, you can, when you're editing your ALU, you can go over here and make it look the way that you want it to look. But when you're all done, your ALU should have all 9 operations: bus 1, bus 2, bus 3, your C out, and your 0 right here. And so you don't really need to hook lights to these, but in bus 3, what we can do in our wiring, I believe there is something called a probe, and a probe will just display its output right there. And then we can also, on these, we can grab inputs, make them 16 data bits wide, and grab another one for bus 2. And then hook up all of your switches onto this right here. Now, it might seem like a lot of work to test it, but first of all, you really want to be sure that your ALU is working correctly before you move on to the next lab. If there's any bugs in here and you don't catch them and fix them, then you're going to have a really hard time in the next lab. All right, now that we have all the 9 inputs, we can test them one at a time. I'm going to test TRA1 first. So we'll go ahead and grab all that poke tool, turn TRA1, and then you should test whatever goes out on bus 1 should be coming out onto bus 3. Okay, so now let's test 2's complement. Remember, we only turn 1 operation on the time. So this is 1. The 2's complement of 1 is all 1, so that's a good test for 2's complement. Subtract, let's try subtracting 1 and 1. So we got subtracting, and if you notice this wire over here, and maybe you do want to hook a probe or an output switch, notice that when the output is 0, our 0 output also turned on. So that's a good test for subtract, and it's a good test that your 0 is working. And now let's do a shift right, and you can turn on these bits right here. And one thing you want to test with your shift right, make sure that this 1 bit, see how it gets copied to 2 spots right here. And you might want to check some other digits with shift right, and then shift left over here. And you can see that this bit comes 1 bit over, like the lowest bit gets shifted left up to there. Okay, and then add, well, let's go ahead and add 3 here and 5. So this is 5, this is 3, and that gives us 8. So that's working great. And then the OR will OR both of these together. So when either one is high, they'll be high there. And then you have the NOT. The NOT should invert all the bits on this bus, bus 2 right there. And I believe the AND operation, I didn't quite try, but the AND operation, and when both of them are a high, then it will be a high, otherwise they're 0. So I kind of tested all 9 operations. So when you go to pass this off, what you need to do first is go to your circuit and show quickly that you've got bus 1, bus 2, all of your 16 bits, bus 3, and your 0 hooked up. That should only take about 30 seconds. Then go to your test ALU and show me each one of those 9 operations that you're getting the correct result. 2's complement of bus 2, 1 is a good test for that. Subtract, you could subtract 2 numbers, make sure you're getting the right output, and so on. And you can keep going, test all your operations, and make sure that that 0 turns high when the output is 0 too. And then that should be a pass off. It might take you 2 to 3 minutes to show all these operations when you go to do your pass off video, and that's okay. But you really should test it a lot more than just what you do in your video to make sure everything's working. Thanks for watching.